Let's start this section with a couple of examples of problems taking into account motional EMF. A jet airplane with a wingspan of 75 meters is flying at 280 meters per second. What is the EMF induced between the wingtips if the vertical component of the Earth's gravity is 3 times 10 to the minus 5 Teslas? Okay, let's look at how we would do this problem. Remember, motional EMF is equal to the field times the length times the velocity. So this is going to be 3 times 10 to the minus 5 times the length, which was 75 meters in this case, times the velocity, which is 280 meters per second. And that, if you do the math, is going to be 0.63 volts. 0.63 volts. The second question, at what speed must a sliding rod in figure 2311, which is in your notes, move to produce an EMF of 1 volt in a 1.5 Tesla field if the rod's length is 30 centimeters? Well, if we take this equation here and now solve this for V, it's going to be E divided by B over L, which in this case is going to be, it's 1 volt divided by B, which is 1.5 times 30 centimeters or 0.3 meters. And if we do the math on this one, we get 2.22 meters per second. Let's move on and talk about something called eddy current and dampening. An eddy current is a motional EMF in a current loop in a conductor. And I'll show you an example of this in just a minute. Magnetic dampening is the drag force on motion caused by eddy currents. So this example right here is the most common way to demonstrate eddy currents and magnetic dampening. And what you have here is 3 different situations. The first of which is a solid metal conductor that is swinging through this magnetic field, and the motion of this magnetic plumb bob is a quick dampening caused by the eddy currents inside this metallic substance. Now if you look at B is a slotted, and then with the slots there is less effect. And then lastly, C is a non-conductor, and non-conductors produce no eddy currents, and therefore there is almost no dampening at all. So let's take a close-up at what happens. In the first situation, we have a solid conductor, and you can see that the magnetic field is moving into the page. The swinging is back and forth through the plane of the page. And you can see the right-hand rule shows that as it swings from left to right, you have a eddy current, a counterclockwise eddy current, which produces a force that is opposite the direction of the velocity. When it reaches the other side or the right side and begins swinging back to the left, the current reverses itself, and again the force opposes the motion. So in both cases, as it swings back and forth, the induced force by the motional EMF causes a drag on this motion, and the pendulum swinging decreases quickly. Now, in the next case with the slotted current, you see that there are eddy currents that happen, but because of the smaller size and this significantly less EMF induced, it causes less dampening. And then obviously, if this is not a conductor at all, it decreases even less. The other thing that happens is that because of the varying places where these slots are, some of these oppose while others do not, and they cancel each other out. Now, dampening can be used to do many things, and one thing that dampening can be used is to separate metallic trash from the rest of the garbage by putting a large magnet underneath a slide, and the non-metallic materials move on and the metallic materials stop due to the magnetic drag. Now, a generator, as we mentioned before, is a device that uses motional EMF to produce an electrical current. In fact, what it does is it converts kinetic energy into electrical energy. And here's a schematic of a generator. Basically, in this case, a person is putting the kinetic energy into the coil. This kinetic energy causes the coil to pass through the magnetic field, and as it passes through, the change in flux produces a current inside this wire. Now, when you have a single wire like this, rotating at a constant angular velocity in a uniform magnetic field, this produces a sinusoidal pattern, which I'll show you a graph of in just a minute. You will remember, as we discussed this before, that during the first half of the rotation, the current is in one direction, and during the second half, the current would be in the other direction. And so it produces a sine wave, much like you see here on the right, where half of the time the produced electrical current is in one direction, in a positive direction, and the other half of the time it is in the negative direction. The actual period can be calculated as 2 times pi, pi being divided by the angular velocity, where f is the frequency in which it passes through. The script E stands for the generated EMF. Now, a true generator, like what we use in real life, has what's called a split ring or a commutator that allows for the electrical current to change direction so that you never have the negative part. So you have pulses of direct current and no negative current. And obviously, the faster this rotation occurs, the pulses are faster and the light doesn't flicker. So let's look at a couple of problems related to generators. Calculate the peak voltage of a generator that rotates its 200-turn, 0.1 meter diameter coil at 3,600 RPM in a 0.8 Tesla field. Now let's look at how we would do this. First of all, we need to calculate omega here. And omega is 3,600 revolutions times, a revolution is 2 pi radians, divided by 60 seconds per minute. And that gives you an angular velocity of 377 radians per second. Now, the E equals the number of turns times the area times the magnetic field, and now instead of V, we would use the angular velocity here, omega. So we have 200 And the area is calculated because it has a circular coil. It's going to be the pi r squared. So pi times 0.05 squared times the magnetic field, which is 0.8 Tesla, and then times the angular velocity, which is 377 radians per second, 77 radians per second. And if you do all of that, you get 474 volts. And that's the peak voltage with the rotation of this. Now, the second problem states that a bicycle generator, those are those little things you put on your tire, rotates at 1875 radians per second and produces a peak voltage of 18 volts. It has a 1 by 3 centimeter rectangular coil in a 0.64 field. So how many turns are in the coil? Now all you have to do is take this formula and now solve it for N. And N is going to equal E divided by A, B, omega. And so E is now equal to 18. The area is 1 by 3 centimeters, or 0.1 by 0.3, which if you do the math here, equals 0.0003 square meters. You have to change everything to meters. And then the field strength is 0.64. And the rotation is 1875 radians per second. The guy's really pumping down the road on this. That's very fast. And so if you do the math here, you get 50 turns. And obviously 50 turns is a practical size for this kind of device. Now let's talk for a minute about something called back EMF. Back EMF is when you have a motor and a motor is moving through a magnetic field, there's an induced current with that motor. And this induced current is in the opposite direction of the current that powers the motor. And so that's why it's called a back EMF. The coil of a DC motor, direct current motor, is represented by a resistor in this scheme. The back EMF is represented as a variable EMF that opposes the one that's driving the motor. And so it's in the opposite direction. The back EMF is 0 when the motor's not moving. And it increases with the increasing rotational velocity or angular velocity of the motor. Now, fortunately, the back EMF tends to be far less than the driving EMF, and so it does not overcome what the motor is trying to do.